I put this up whenever I talk about food policies. This is my disclaimer. If you need a lawyer, find a lawyer. I'm doing this I think it's really necessary to understand the policies, to understand this subject. So I'm going to give my interpretation of them to you. So, and this is the main one. This is section 342A1. This is what defines what an adulterated food is. It's the basis of almost all actions that are taken by FDA against foods. And these are the exact wording, and I'm not going to go through and read this. Instead, I'm going to jump over to the next slide and a couple of important things to note about section 342. One is that there's a differential requirement based on whether you're dealing with a material that has been added or if you're dealing with a material that's naturally occurring. And it's a very large difference between these two, where the requirement for something that is added, something that involves the hand of man, and that's the term that's used in regulatory circles, is that it may render it injurious to health. And the key word there is may. As opposed to the non-added substances, here it does not ordinarily render the food injurious. And this is a huge difference when you're talking about the toxicology of these compounds. Also might note that within the later sections of 342, it also indicates that the addition of substances such as pesticides, food additives, etc., are not adulterated as long as you use them within the precepts of the pre-market approval. And so these are the key things that you deal with when you're going through. And what you have to do is basically pull this reg out, and you have to go through it. And for those of you that haven't read federal codes, they're probably nothing more boring and harder to go through, and that's why food lawyers make a lot of money. But these are the sections that you would have to with different substances that are purposely added. Okay, the other thing about this is that within the Act, you have the possibility of formally setting tolerances for other compounds under 346A, including naturally occurring substances, and it's not done. As far as I know, other than the food additives, etc., stuff that falls under there have never been a tolerance that has been established. Instead, FDA generally relies on action levels or related guidance criteria. And they do this under the system of either regulatory discretion, which has been upheld by the Supreme Court, or the use of thresholds of regulatory concern for certain substances. So this is where they can have a little wiggle room as they go through. Okay, I'm going to jump into my two examples, and I'm using these as examples of where risk-benefit analysis have been used, and I'm going to follow up Rick on in terms of using methylmercury is probably one of the most intensely and most controversial. As you probably all aware, methylmercury bioaccumulates. It's originally produced from inorganic mercury, is converted to methylmercury as a result of anaerobic bacteria, and it concentrates as you go up the food chain. And so the biggest fish have the largest amounts of methylmercury. So it actually starts down at creel and then it moves its way up. The important thing about here is that there's actually multiple etiologies. Almost all methylmercury that humans are exposed to comes as part of the diet, and it's associated almost exclusively with seafood. The original source, as is indicated, is inorganic, that's converted, and we have two differing etiologies depending on the source. We have the source that are associated with fresh water and certain estuarian environments, and this is a combination of both natural contamination and as a result of pollution. So here you can make a case for the hand of man. So you follow the more stringent criteria. On the other hand, when you're dealing with pelagic sea fish, the ones out in the deep ocean, these are almost exclusively obtain their methylmercury as a result of mercury coming originally from volcanoes. There is no hand of man. And so this would be, theoretically at least, fall under a different criteria within the law. Okay, so methylmercury toxicity, what you're most concerned about here, the one that is most sensitive in terms of causing adverse effects, is chronic low exposures. And these involve two different areas. One is developmental effects in young children, resulting in some fairly subtle changes in things like motor skills, language skills, mental function, attention, ability to stay focused, etc. As opposed to the other area which occurs in adults, and this is primarily in association with the risk of cardiovascular disease. And then you run into the problem that every study of seafood, and remember, this is associated with seafood, so theoretically you should always do these experiments with seafood. And one, you have a problem, you can't have a test animal, there's just no good test animal for cognition. So you're stuck with doing humans and epidemiological studies, and all of those studies are inherently confounded because of the confounding effects of omega-3 fatty acids and selenium, which tend to mitigate the effects of methylmercury. So you've got a situation where you're dealing with something that inherently is there and at some point is going to interfere with your analysis. Okay, I might note this is the draft FDA risk assessment. It is available online. It has never been finalized, but the risk assessment for any of you that are studying that are available, and it's a very good read. It's a well done, and I do have to have a bias there. I was the primary reviewer on it when it was being developed, so I have a certain bias on it. But it is there, and I downloaded it just before this meeting, so you can get it. There have been a couple of key epidemiologic studies. I'm going to cut to the chase. Fish consumption has a very positive effect on neurological development when we're talking about cognition for young children. If you get too little fish in your diet, you're at risk for not having optimal cognition. If you get too much, particularly if you get too much methylmercury in the fish that you're eating, this is offset and you actually have decreases. So you've got two sides in a natural occurring system. Same thing that happens when you're dealing with a meta-analysis of the published literature on CHD effects. And again, it's the same kind of situation. If you don't eat enough fish, you're at increased risk of cardiovascular disease because of the need for selenium and omega-3 fatty acids, particularly if that's your primary source. If you get too much methylmercury, particularly in freshwater fish where there may not be a lot of omega-3 fatty acids, you go to the other side. So, how do you manage that kind of situation? Well, as Rich has already indicated, the way that they're approaching it now is labeling to reduce the frequency or extent of consumption of fish. Okay, that's not off the top of my head, I can think of at least 3 other ways of doing it. Limit the size of the fish that can be marketed. Remember, if you get rid of big fish, you largely have this problem go away. You could differentiate fish from high and low risk locations. Or the last one, it's the ideal way would actually test your fish for methylmercury before you sold it. Now, I wouldn't recommend it for sardines. You could go broke trying to do it. On the other hand, if you see in this picture, if you're buying a fish that costs $750,000, that's one fish, you probably can afford to spend a little bit on analyzing it for methylmercury. So that's a world-size bluefin tuna that was just recently sold in auction. I might note this continues to be a real issue if you haven't been paying attention because you were down here enjoying the warm weather. Over the past weekend, 120 countries actually got together and started this big multinational thing on reducing methylmercury emissions in order to get the levels in our food down, in our seafood down. Okay, let's pick up another quick example, oxychloro compounds. And so what's an oxychloro compound? Well, basically an oxychloro compound is the disinfectants we use to treat our water, to wash our foods in, to get rid of bacteria, etc. And this came about as a result of some action that was originally proposed by some of the Scandinavian countries in the Codex, Committee on Contaminants. And they wanted to severely limit the exposure of foods to active chlorines because they were concerned about the generation of carcinogenic compounds. And so they proposed a severely limit these compounds. And that got over, and I was actually the head of the U.S. delegation at the time. This hit the Committee on Food Hygiene, and food hygiene, for once, was almost unanimous in its response. And anytime you get 140 countries to agree on anything is a big stride. And they were just livid about, what are you kidding? This is our primary tool for controlling infectious diseases around the world, and you want to eliminate its use with foods? And so basically, it's recommended strongly to Codex Alimentarius, the parent body, that contaminants not be allowed to do anything until there was a scientific evaluation. So anyway, there was. And FAO and WHO brought together experts from around the world. They did what they called a benefits and risk evaluation on the use of chlorine-containing compounds. This is where the report is available, and it can be downloaded. Also, it's important to read, before you read the report, the 2 charges from the different committees that was given to them on what they should be doing. And this was the goal of it, was to determine whether or not the risk of chemical residues in food products had a greater impact or a more important impact than the benefits that were achieved in relation to lowering microbial hazards. And they did a nice job of considering the full range. They looked at the efficacy of the chlorine treatments, the availability of alternative treatments, the treatment scenarios that it's currently being used, and they looked at a variety of different commodities. So the basic approach was to do some semi-quantitative risk assessments, not enough data to do a fully quantitative. They used a series of what-if scenarios in terms of the different kinds of residue levels that you're going to see. And then they did what they referred to as a risk-benefit evaluation. I might note, I have a different criterion for this, and I consider this a risk analysis, not a risk-benefit analysis or assessment. So these were the recommendations that came out of it. There were a couple of general ones there at the top, but basically they said, based on the available data that they had at the time, there was no indication that there was a toxicological concern at this point. They did indicate that there was evidence that there was a protection that was being provided in terms of knocking down pathogenic organisms. So last time I heard, the original proposal at CCFAC has been withdrawn, and they're not doing this approach anymore. But this is one of the examples of where there has been a very formal international risk assessment that's looked at this, considering conflicting risks. So that moves me on to using risk-benefit assessments in chemical food safety. And there's certainly, particularly among a lot of the people in this audience, there's been renewed interest in being able to consider benefits in chemical food safety issues, similar to what is done with drugs, medical devices, biologics, etc. The major argument, of course, for pushing this is that you get a much more informed decision if you look at this entire societal impact of a question that you're dealing with. And I might note, this is not new. And I guess maybe one of the things that's going to cloud my judgment in terms of how I look at it in terms of approaches, when I was doing my master's degree, and I did my master's degree on nitrosamines and nitrite in microorganisms. And this was a time, and it predates most people in this, when they were about ready, not everybody, I can see a couple that were around here still. They were going to ban the use of sodium nitrate in foods because of the fact that there was a potential for producing nitrosamines, generally in low levels, but if you did it wrong, in higher levels. And there was a big discussion about benefits, and people were moaning the loss of the hot dog and hams, etc. And it really looked like they were going to drastically decrease the use of sodium nitrite in the meat industry particularly, but not just meats. Until a bunch of microbiologists said, if you do that, you're going to increase the risk of Clostridium botulinum in these products to an incredibly high degree, because that's what's protecting your food right now. And as soon as it got down to one risk versus another risk, okay, it stopped. And people got busy to find how they could pragmatically reduce the level of nitrosamine formation, how they could minimize or come up with other systems, and it worked. And so that's what clouds my judgment, because there's a number of things that are going to prevent you from taking a risk-benefit approach, at least here in the United States. One is there's a long history of safety-only considerations. They don't do benefits. They do risk. That the consumer's risk tolerance is much less for foods than it is for drugs. Things you can get away with on drugs, you would never be allowed to do by consumers for foods. They put them in two different places in terms of risk perception. 3, it is extremely difficult to articulate benefits to the consumer when you're doing this type of risk-benefit analysis. If you don't think that's true, think about genetically modified foods, and they're still looking for a good communication on how to tell consumers that they're getting something for the inclusion of this types of food. And then the real issue here is, why consider tolerances when there's a surplus production of foods? You don't meet the concept called avoidability in terms of getting a risk-benefit analysis. And then finally, it's really difficult to quantify benefits and then compare them to risk. Just a word on avoidability. This may be this is a risk management concept, and it basically says, why are you considering benefits when you can just substitute other things? So for methylmercury, substitute one type of fish for another. You avoid the problem. The other thing that's apparent here, you can make a good case that fish is very helpful in terms of, both cognition and cardiac disease. The problem is this has got to be balanced out with the fact that the majority of the omega-3 fatty acids that you're using to supplement foods right now doesn't come from fish. It comes from other things. It's plant omega-3s. And they haven't quite shown that they provide the same types of benefits as fish does. Oxychloro compounds, the same thing. Well, why don't you use a peroxide-based disinfectant? Why don't you produce foods that were free of pathogens in the first place, and you wouldn't have to treat them? And trust me, I don't know how many times I've heard that dealing with people. Okay, so the alternate approach is, instead of doing a risk-benefit analysis, you should be doing a risk-risk evaluation. Get it in terms of two competing risks. Okay, it's more easily quantified and specific. You can develop a common metric for that. In fact, a common metric already exists. You have a much stronger imperative, because you're dealing with two things that scare the population, that come up with a situation where you're finding an optimal solution. Okay, so the key difference here is not that you're ignoring benefits. What you're doing is you're reparameterizing it so that you're dealing with risk. So what you're looking for here, and this is a very simple graphic demonstration of it, the benefits expressed as a risk, so as the concentration goes up, it goes down. The naturally occurring toxicant, it increases, its toxicity increases with concentration. You're defining an ideal state, and then you're trying to get as close as possible to that ideal state. With the two lines, you're intersecting them, and that's how you would approach a risk-risk trade-off when coming up with a decision. This is something that's already being done in the nutrition arena. I might note this is a classic nutritional risk assessment where if you don't get enough, you die. If you get too much, you might die. And what you're looking for is that middle ground, the sort of the sweet spot. So we already have a lot of precedent for doing these approaches. Now, I might note, nutritionists really hate the fact that we refer to this as a risk. They still think they're giving benefits, but what you're defining as an ideal state, and anything less than that is a risk on either side. We are increasingly using a metric that allows us to do these, to do comparative risk assessments. And they go like this. And so what we're doing is trying to consider other risks. And these are what are commonly referred as risk trade-offs. Chlorine is one of those. I might note this is what we're doing in risk ranking now when we're doing it quantitatively. I might note for any of you that actually want to try it, FDA just released a new tool, a really super set of programs that allow you to do online risk assessments, including some fairly sophisticated Monte Carlo analyses. Okay, unintended consequences. I'm going to burn through this in 3 minutes, so I get there. You should always do, whenever you try something new, you should think about what happens when you've put it into place that you weren't expecting. So the bottom line on this one is if you prove to them that you can do this complex math, they're going to expect you to do it all the time. And what you're going to do is you're going to get into things like my example here, which is arsenic. It's all over the media. And arsenic is one of the most commonly used ones. It's based on the only standards we have right now are for either drinking water or for bottled water. It's the same one. It's an EPA, FDA thing. And basically, if you use a 70-kilogram man and you start looking at daily intake, it's basically what that requirement is a 286 nanogram per gram body weight. That's the daily intake that's acceptable. However, what happens if you go through and you target a 4-month-old infant? Has a diet of 4 things, either breast milk, water, and maybe a little apple juice and rice cereal. And you start looking at the levels of these. So I just want to go through this. These are some of the intakes. Again, I'll give you these slides. This is a back-of-the-envelope type of a risk assessment. The primary source of arsenic in the diet is water, either from natural sources or left over from the use of arsenic pesticides in certain areas of the country. This is the type of levels in the diet that we would expect from each of these criteria. And if you start doing the calculations, which I just simply took the inorganic arsenic, added the 4 sources up to get them to come out. I did only powdered infant formula in this one, but I did look at a couple different scenarios. Let me just jump to them. If I looked at inorganic nitrogen for, it's not wanting me to go back, well water. And what I got was 515. If I went to upper limit well water, the worst of those wells, I got up here. So this is an area where all of a sudden you got to start dealing with it. And the big question here, and a very practical one, is who gets the tolerance? Which one of those 4 foods, bottled water, powdered infant formula, apple juice, or rice cereal, actually gets to do it? Because you're not going to make the limit if everybody tries to take it. So anyway, I've had to go fairly rapidly through here. I just want to summarize by saying that I think this is incredibly important that this type of work has been done. But in terms of practical applications, think about risk analyses as opposed to trying to define benefits, which is pretty hard, and go that way. Thank you.